All right, our last unit from this, or last video, sorry, from this unit, we've talked a little bit about identities. We've talked about messing around with double angles and half angles and sums of angles and all that stuff. And we're going to shift gears a little bit and just start solving some equations that have some trigonometry in them. This is maybe one of the more useful skills that you'll transfer to other classes. So when you go off to your calculus classes or your physics classes or engineering classes or things like that, this skill of solving equations with trigonometry in them is going to be really important. I teach a bunch of calculus classes as well, and so this is always one of the things that I'm encouraging students to go back and remember and relearn if they need to, because it shows up a bunch. So this first bullet point is really like the most basic fundamental thing. It's not necessarily the easiest thing, but it's a really important fundamental skill that we'll need to have for the remainder of this class, but also for other classes. That's probably one of the things that will transfer the most. Then we'll end up looking at this idea of like multiple angles. We'll solve equations in quadratic forms or by factoring or things like that, and then we use some identities to solve some stuff. But let's start with the first basic setup. How do we solve a trigonometric equation? So first, what is a trigonometric equation? This is just some sort of an equation that involves a trigonometric expression with a variable, but the main key here is that the variable now is the input of the trigonometric function. So you're going to be having things like sine x, cosine x, all that kind of stuff floating around in your equations. And when we solve for x, that means that x is likely going to be some sort of an angle here, because we're putting angles into these trig functions. And so our answers are all going to be angles that make our equation work. These angles will mostly represent using radians. So we will very, very frequently use degrees on this. Most of the time we're going to be doing things in radians. We have to be careful when we use inverse functions here, because they can limit the number of solutions that we get. For instance, if we were to look at this equation and solve it by using a square root, then we'll say, all right, the square root of x squared equals the square root of 9. So we get that x is equal to 3. But we know that that's not right. We're missing one of the possibilities, because negative 3 is also a solution here. So our way around that is by making sure that when you do square roots, when you're working with equations, we use this little plus or minus business. So plus or minus 3 are actually both of the possible solutions that we have. With inverse functions, they do a similar type of thing. Remember that they restrict the types of angles that they'll give. So sine inverse only spits out angles that are in the first or fourth quadrant, because we look at the varying y values there, and so we skip the second and third quadrant angles. For cosine inverse, we do a similar thing, but it only gives us the angles in the first two quadrants. So if you use inverse functions, you just have to be careful about the fact that you're missing half of your angles, because we've got these other quadrants where those angles will give you the same type of thing. So because of that, I'll stay away from inverses. You can use them if you'd like, but I won't really show that stuff formally, because they do restrict the number of solutions that we get. Most of our equations are going to have an infinite number of solutions, because we can always find a coterminal angle. For instance, you could just revolve around your circle again, end up at the exact same spot, and all your outputs of your trig functions are going to be the same, even though you have a different angle. So, because we can revolve around our circle an infinite number of times, we get an infinite number of coterminal angles, and so we have an infinite number of solutions. Because of this, sometimes our setups will just give us a little restriction and say, you know what? Let's not consider all the different possible revolutions. Let's just look at the stuff between 0 and 2 pi, or maybe between negative pi and pi, or something like that. So keep an eye out for that when it exists. I think the best way of getting into this is just starting off with a basic example. So let's take a look. This is a pretty small equation. There's not a lot going on here, and my guess is that your intuition will kick in and you could do this. You go ahead and divide both sides by 2 to get that cosine x by itself. And so suddenly you've got cosine x equals a half. And we can start thinking about, okay, what types of angles are going to make this work? What types of x values could we put into the cosine to get half out of this? And you could see pretty easily what that's going to be. We know that pi over 3 is going to be a solution. Let me draw it real quick. Pi over 3 is going to be a solution because there's a nice point right here at half root 3 over 2, where the x value of this point is a half. So if we're thinking about the unit circle, then the cosine of that angle is going to be a half, and we know that this angle is pi over 3. So, bang, cosine of pi over 3 is equal to half. We know that pi over 3 is a solution, but we also know that it's not the only one. There's another point with the x value of a half. It's the one that's reflected below the x-axis. It's 5 pi over 3. So let me go ahead and draw that picture again. Whoops. I want my straight line. There we go. So we end up with two angles. We get that first one that we looked at, but we also get this second one down here where the point is reflected. But since that point has the same x-coordinate, it just has a negative y-coordinate. That means the cosine output is the same. And so still, cosine of 5 pi over 3 is a half, and so that's another solution. So our reference angle in this case is pi over 3. We're pi over 3 less than 2 pi, so we end up with 5 pi over 3. Cool. But still, there's more. Because we can just look at coterminal angles. We can go around and around and around in our circle as many times as you'd like. We could say, instead of just stopping at pi over 3, or instead of just stopping at 5 pi over 3, we could go around to right here. And we could say, well, that's pi over 3 plus 2 pi, so that's, pi over 3 plus 2 pi, so that's 7 pi over 3. And we could not stop there if you wanted. We could keep going around. And then this is pi over 3 less than 2 revolutions, so less than 4 pi, so that's 11 pi over 3. And we could keep doing that. And if you wanted, you could also do the negative revolutions. Right there is negative pi over 3. And if you kept going around in the negative direction, you've got negative 5 pi over 3. Etc., etc., etc. And then you also have these positive versions in here. So instead of writing out the infinite number of solutions, what we'll do then is just write a little pattern that represents them. So this is what this looks like normally. We'll say x can be pi over 3, that first one, plus 2n pi, or 5 pi over 3, that second one, plus 2n pi, where 2n pi is just some number of revolutions around the circle. So n is some integer. We normally won't write this part here because we'll just assume that we know what n is. So when we say 2n pi, or sometimes people will say 2k pi or things like that, we're just saying it's some multiple of 2 pi. 2 pi is a whole revolution around the circle. So we're just doing some number of revolutions around the circle. Now n could be 0, in which case we just get our two solutions right here. But if n is anything else, then we get all those other angles that we were looking at. And so this is a nice way of representing the infinite number of solutions. Find the number of solutions that are in a single revolution, and then just add this 2n pi that says, okay, keep going around the circle a whole bunch of times. Neat. That's our basic fundamental skill that we should be able to do. Find some angles, make sure that you can extrapolate that to get all the possibilities by adding in this 2n pi to get the infinite number of revolutions around a circle. So, what if we make it a little bit harder? What if we look at something that has more than just two answers, and so maybe it has different number of solutions in a single revolution? So here's a more tricky equation right here. And also notice I've given us this restriction. I've said 0 is going to be less than x, and that's going to be less than 2 pi. Really, we're going to say our angles are in the first revolution. So now we're not really going to worry too much about the whole plus 2n pi thing. What we're going to do is we're going to, at the very end of things, figure out how many angles are fit in that first revolution for x, and we'll just take those as our answer. For now, your intuition probably will kick in. You can solve that underlined equation for just sine 2x. That's our trig function. Let's move that 3 sine 2x over to the other side, add 1 to both sides, divide, all that same kind of stuff. So go ahead and do that, or you can just kind of imagine what that's going to look like. I'm going to skip ahead in a sec. All right, that's probably good enough. There we go. So this is what this looks like. We end up with sine of 2x equals negative half. So now we can say, okay, what angle 2x is going to give us negative half when you put it into the sine function? That shouldn't be too bad for us to do, but sometimes it can be a little bit weird to think about that 2x. So what I'll do sometimes is I'll just take that 2x and I'll say, instead of looking at 2x, let's let theta be 2x. then we just end up with sine of theta equals negative half. And that's a little bit easier for us to think about. We don't have to think about what's going on with that doubling angle on the inside or anything weird like that. So what angles give us an output for sine that's negative half? Well, we know what quadrants we're going to be in now. We're going to be in the third and the fourth quadrant because sine is the y value on the unit circle and it's negative. So let me just draw this. We're going to look at these angles right here. Not a great drawing of them, but oh well, that's pretty close. And the whole point is that this point is negative root 3 over 2, negative half. And this point is positive root 3 over 2, negative half. The y value on both of these is negative half. So we can try and figure out what these angles are. The reference angle is the same in both of these. It's pi over 6. So this is pi over 6 less than 2 pi, and this is pi over 6 more than pi. So our angles for theta are going to be 7 pi over 6 and 11 pi over 6. I'm just subtracting pi over 6 or adding pi over 6 to either pi or 2 pi. But again, we know those aren't the only ones. We can do all the revolutions around here. So this is what we look like. We have those two, but then 19 pi over 6 is really 7 pi over 6 plus 2 pi. 11 pi over 6, if we add 2 pi to that, that's going to be 23 pi over 6, and then we could keep going, etc., etc., etc. Also, you'll notice that we can subtract 2 pi. And we get these other angles. And you could keep doing that and get an infinite number of angles. Those are our angles theta. Every now and then, people will go back and they'll say, wait a second, we only want the stuff in between 0 and 2 pi, so don't we just knock out all these other angles? Don't we say, well, that's not in between, that's not in between, that's not in between, that's not in between, and that's not in between? The problem with this is that these are values for theta, and we want x to be in between 0 and 2 pi. So we should go back and say, well, maybe theta is going to keep those things. X might be something different. So what I'm going to do is I'm just going to use this little substitution again. I'm going to say, screw it. Let's just write this with 2x instead. So this is what this looks like. So here's our 2x equals those same angles. And now it's pretty easy to see how to solve for x. We're just going to divide everything by 2. So if you divide this by 2 and you divide everything over here by 2, that's going to change your denominator. Your denominator is going to go from 6 to 12 now. And so you're going to get a whole bunch of new angles. So here's all your angles. And now we can start going back to this restriction that we had and say, well, x has to be in between 0 and 2 pi. So now let's start knocking out those. This negative angle is still gone. This negative angle is still gone. Maybe I'll make that a clear. There we go. 7 pi over 12 is in between 0 and 2 pi. 11 pi over 12 is in between 0 and 2 pi because I'm thinking in my head 2 pi is 24 pi over 12. 19 pi over 12 is in there. 23 pi over 12 is in there, but 31 pi over 12 isn't. And then all the ones after won't be. So now, instead of just two solutions being left, instead of looking at these and saying, well, we had 7 pi over 6 and 11 pi over 6, when we solve for x by dividing all these things in half, because we had this 2x on the inside of our sine function, we end up with 4 possibilities. And so, since we're looking at angles in between 0 and 2 pi, here's our 4 possible solutions that we have. Cool. So, whenever you've got something composed on the inside of your sine function, I recommend doing this little variable substitution and then solving for x later. It's a little bit easier to keep track of. Some people can skip that and they'll just jump right to this spot and say, okay, 2x is going to equal all those things and then solve for x. But using this restriction can sometimes be a little bit tricky with that. So just make sure that you actually do find values for x, and that's when you look at the limitations. Less basic example, but still not crazy. What you'll notice is that there's really 2 parts for this. Really, all we're looking at is isolating or solving for the trigonometric function. So whether it's a cosine of x or a sine of 2x or whatever, get all that stuff together, make it equal something. Then find the angles that work. So whether that's as easy as that first one where we just said, oh, cosine of x was equal to whatever it was, or the second one where we had sine of 2x and we had to do that little variable substitution, it's just 2 steps. Solve for the trig function, find the angles that work. So we have different types of trigonometric equations. The ones that we just looked at we call linear, and that's because if you go back to those, the degree on any of the trig functions is 1. Meaning there's no visible exponents. There's not like a cosine cubed of x or something like that. Oh, excuse me. We're just looking at straight up sine and cosine functions. Since there's no visible exponent, we know the exponent is just 1. So we call that linear. A quadratic trigonometric equation has degree 2 trigonometric terms, meaning there's exponents on things. Just like if you were looking at a parabola, we call that a quadratic function, or if you had an equation set up, it's a quadratic equation because those have degree 2 on our variables. So if it's a trigonometric equation and it's quadratic, then it's got a degree 2 on the trigonometric term. So how do we do this? We're going to end up probably doing a little bit of variable substitution to just make it look a little cleaner, a little bit more obvious. And then we just have to think about how do we solve normal quadratic equations. We're going to be doing some factoring. We maybe will have to use the quadratic formula. Probably not in this case, in this video, but that's something that you can keep in the back of your mind if you'd like. So we're going to focus a lot on the factoring part and the variable substitution part. And the quadratic formula, that's if you're stuck. All right, so let's see how this works. So I've got the setup stuff already. I'll show you what I mean by the variable substitution. So here's your equation. Notice degree 2 on the sine function here. And so we call this, hey, this is a quadratic trigonometric equation. Because this looks really busy and complicated, this is what I mean by a variable substitution. We're going to go ahead and say, every time you see a sine x, let's just put in u on there. U is a pretty common variable to use for variable substitutions. You'll get used to seeing that a bunch in classes like this or in calculus or things like that. There's no real rhyme or reason to it. Just that's the normal variable that we pick. Just like x is the normal input variable that we pick and y is the normal output variable. You can pick other things if you'd like. But now, if we write it with u in place of sine, this ends up just looking like a regular old quadratic equation. And it's easier to visualize, and it's a little easier to factor. We know that if we can factor this thing and set it equal to 0, then we can just look at what each of the factors are and get solutions from there. If you can't factor, you could use the quadratic formula on this. Negative b plus or minus the square root of b squared minus 4ac all over 2a. I think I said that right. We probably have that rattling around in the back of your mind. So you could go ahead and plug in these coefficients into that formula if you'd like, but we can factor this. So I'm going to factor it. You should too. Go ahead and do that. See if you can solve this and see what values for you are going to work, and then we'll pick this up from there. Pause the video, give yourself some time, and give that a shot. All right, you're probably back by now. All right, let's do it. So this is what it looks like when we factor. So I went ahead and factored this into 2u plus 1, u minus 1. If you do the distributive property and multiply it out, there's your 2u squared. There's your u. And negative 2u, that gives you a negative u, and then 1 times negative 1 is negative 1. So you can check this by just doing the distributive property, multiplying it all out. And now we can pretty clearly see that what we're really doing is setting each of these things equal to 0. So u is negative half, and for this one we say u minus 1 is equal to 0, so u equals 1. So these are our two solutions that we have. Cool. But these solutions are actually what sine x is. And so really, we've just done the first part of that little two-step thing that we had on that darker screen. We solved for the trigonometric function here. We still have to find the angles that are actually going to work in this case. So what we really have now is sine x equals negative half, and sine x equals 1. And both of those we should be able to do. So here's our kind of stopping point now. We've got these two little trigonometric equations that we want to solve, and they shouldn't be too hard. I'm going to give you a little bit to figure out what your basic angles are and all that kind of stuff. See if you can figure out what values are going to make sine x equal -½ and what values are going to make sine x equal 1. So again, pause the video, see if you can fill in the rest. You back yet? Here we go. So I'll do this first equation over here. We've got 7 pi over 6 and 11 pi over 6. And for this one, we know that sine being 1 means that our y value is 1, meaning we are existing right here on our unit circle. Bang! 90 degrees, pi over 2 radians. For sine of x equals -½ we've got, again, these angles right here. There we go. So the coordinates of this one are 0, 1. The coordinates of this one are -√3/2, -½ and √3/2, -½ So there's your two y values for that one. There's your y value for your other one. There we go. Now, these are just the three angles in that first revolution. So we can add all of our revolutions around here because we did not have a restriction on just being between 0 and 2 pi. So really our solutions look like this. 7 pi over 6 plus that 2n pi, or 11 pi over 6 plus 2n pi, or pi over 2 plus 2n pi. So we have an infinite number of solutions for this. So the ending really feels the same no matter what. Once you have these equations figured out, it's the exact same thing as if you just started with those, right? That real basic example was pretty much this type of thing. So the hard part is getting that trigonometric function by itself, isolating that. And in this case, we had to do all that factoring to do it. If you wanted, you could skip right to this by factoring in terms of sine and saying 2 sine x plus 1 times sine x minus 1. That's really this step, but instead of use, it's all that sine x stuff. So if you want to factor it with the sine x's still in there and you can kind of visualize that, feel free. But for some people, this variable substitution is really key there. So that's what we've got. We can do factoring in a bunch of other ways too. So notice something like this. This is not necessarily quadratic, although you'll notice that you do have two trig functions in the same term, sine x and tangent x. So while it doesn't have degree 2, while it's not a degree 2 term, if you think about that other degree 2 term as like when it was sine squared, that's really sine of x times sine of x. We have a similar thing here. So we're going to have to do some factoring. Let's go ahead and take this, move it over to the other side, and then what we'll notice is that we're going to have some common factors that we can do. So here we go. I moved my sine x over, so I subtracted. And then sine x is a common factor here, so I just pulled it out. So now I've got sine x times tangent x minus 1 equals 0. We do have this restriction that we'll keep in mind, but we can go ahead and kind of fill in the rest from here. Now we've got sine x equals 0, or tangent x minus 1 equals 0, which means tangent x equals 1. So we end up with these two trigonometric equations to solve. And again, we're just down to figuring out what values are going to give us all this stuff. For sine x equaling 0, that means that the y value is going to be 0. And so we've got 2 points, one right here and one right here. So we've got 0 and pi here. We know we're not going to do all the coterminal stuff because we only want the one revolution. Notice it's just less than, not less than or equal to 2 pi. So we won't actually include 2 pi on here. We'll say 0 instead. That's the angle that we'll include. So 0 and pi will work. And then for this tangent one, remember that's when sine and cosine are the same. That's when we have these nice isosceles triangles, and they're going to end up being the same sign. So bang right here and bang right there. And so if we draw those points, I should put the coordinates on this. That's 1, 0. That's -1, 0 over there. And then our coordinates over here are, you could think it's √2/2, √2/2, And this one here is negative root 2 over 2, negative root 2 over 2. So the x and the y values are the same, meaning your tangent is going to be 1. And so x, in this case, is going to be pi over 4 and 5 pi over 4. And we won't worry about all the coterminal ones because, again, we're just looking at ones in that first revolution. So I think I summarized this. Yeah. So we have 4 values. Oops. I missed my spot there. Oh, my gosh. Let me just highlight it. That'll be easier. So x is either 0 pi over 4 pi or 5 pi over 4. Those are the 4 options that we have that'll make this equation work. So while this wasn't perfectly like a nice little quadratic thing because it doesn't have a degree 2 on there, this term is kind of degree 2 because it's 2 trig functions multiplied together. Outside of this, we can use some identities to do some things. So you might notice that there's some Pythagorean identities that you can do. Those are really helpful when you have something that's quadratic, but you've got 2 different trig functions on there. So I'll show you an example where there's like a sine squared and a cosine in the same thing. And what we can do is we can convert the sine squared over to cosine squared. So then we have just a nice normal quadratic thing. We can do a variable substitution, all that stuff. A double angle identity is really helpful because we know that sine of 2x is equal to sine x cosine x. So if you see this term floating around and we don't really know how to deal with it because there's no common factors, you could also just switch that out and make it just sine 2x. Look for anything really that looks like it's really complicated, or if it looks familiar from an identity, that's helpful. If you really wanted, you could go back to something like this and try and think about what sine x tangent x is and see if there's some identity that you could build out of this. In this case, there's not really anything helpful. You finding that common factor is more helpful. But if there wasn't a common factor, then maybe you could just do some rewriting and build your own identity like we did at the very beginning of this unit. So keep an eye out for those kinds of things. And I think I got one example to show you. I'll show you the quadratic one. So here, quadratic equation, because this is degree 2, but notice we have a sine function and we have a cosine function, not the same type. That means it's going to be hard to do variable substitution. We can't just say, let u be sine of x, and then we have u squared and a 3u or anything like that. So what we're going to do is we're going to use the Pythagorean identity here, because our Pythagorean identities say, in this case, sine squared x plus cosine squared x equals 1, which means sine squared x is 1 minus cosine squared x. So what we're going to do is we're going to take this and we're going to plug that in place for your sine squared x, and then all of our trig functions will be cosines. So that'll be really helpful for us. So this is what that looks like. 3 minus sine squared x minus 3 cosine x equals 0. We're going to take this, swap it out, throw it in parentheses to make sure our signs work out nicely, our positive negative signs, not the trig function signs. And then when we subtract, we've got 3 minus 1, that's 2, and then we have minus that negative cosine squared, so that's why this turns into a plus here. So then we have a cosine squared, a negative 3 cosine, and a 2. I just jumbled up the order because I like putting them in this kind of leading order. Pause the video and see if you can do this. If you want to do a variable substitution, I'll just show you what that looks like. This will be u squared minus 3u plus 2 equals 0. See if you can factor this, see if you can solve it, and go from there. Are you done? All right, let's try it. So hopefully you factored this into u minus 2, u minus 1, or cosine x minus 2, cosine x minus 1. Again, do the distributive property and check it out if you want. Cosine of x times cosine of x is cosine squared. Cosine of x times negative 1, and then negative 2 times cosine of x. Well, there's a negative cosine x and a negative 2 cosine of x. That's your negative 3 cosine x, and then negative 2 times negative 1 is positive 2. Cool. All this to say, here, cosine x equals 2, or cosine x equals 1. This is weird. Why is that weird? Think about that for a bit. I'm not going to answer that yet. Hopefully you're still thinking. If you want to pause this, feel free. I say that that's weird. How come? Hopefully you know. It's weird because the values that come out of our cosine function are trapped in between negative 1 and 1. So are there any angles that make cosine x equals 2? No. There's not any angle that we can think of that's going to spit out 2 from our cosine function. So let me just write that. This is impossible. There aren't any angles that we can put in for x that will make I'll just say cosine x equal 2. And that's because our values for cosine of x, the outputs of these are in this interval. That's the range of our cosine function. So that's a little bit interesting to look for. What this means is that this solution we do not have to think about. That's an impossible task for us. Here, though, we can think about this one. When cosine of x equals 1, that's the x value equaling 1, and so that's this angle right here. And so this ends up being 0 or 2 pi or 4 pi or anything like that. And so we can go ahead and get some solutions out of this. Oh, crap, and I changed this. Never mind. So let me erase this. Let me get a new one in here. So x is equal to 0 or 2 pi or 4 pi, which we can say is just 2n pi. Really, it's 0 plus 2n pi. It's all the coterminal angles with 0. Maybe I'll write that real quick. And I'll update the notes on there. I think I changed the example, and so we mixed up that. So anyways, those are our possible solutions that we have in this case. So what's important out of all of this? What are the things that we really need to be taking care of here? First, it's just this basic level of understanding of how to solve one of these equations. We're isolating our trig functions, we're getting little mini equations there, and then we have to be able to get at angles that are going to give us the correct outputs for those things. So we really need to know some of those recognizable angles. If we don't know them, then it gets a little bit tricky. You can either use some inverse trig functions, or you can think about intersection points of graphs and things, which is a little tricky. If you want to see more about that, take a look at the text. I'm not going to talk too much about it because it's not that important. But solving those trigonometric equations is really helpful. We have to be careful when we end up with those coefficients inside of our trig function. Like in our example, we had that sine of 2x. We have to be careful about those. Do a little variable substitution if you really need to, and then make sure that you actually do solve for x out of that. Make sure that you find what angles that you can put in for x that will get doubled or tripled or whatever based on the coefficient on the inside that will do what you want them to do. Recognizing those quadratic forms, trig identities, things like that, those are really helpful. But the most important thing is knowing the basic ideas about isolating the trig function and then finding the angles that's going to work for you. If there are restrictions on those angles, like it's got to exist between 0 and 2 pi, then you don't have to worry about the infinite number of coterminal angles. But other than that, keep an eye on the fact that we can have an infinite number of coterminal angles that will also give us those same results. So we likely have an infinite number of solutions on here. Dig into the text. I think they do a really nice job of clearing up some of this stuff or just explaining it in different words or anything like that. And if you've got questions, feel free to let me know. Put something up in the message board, all that kind of stuff. So good luck, everybody.